Morning, good afternoon, good evening, everybody, wherever you join this conference. On behalf of co-authors Siahaan, Patrick Wong, Muttuvel, I would like to thank ICGE2020 for this opportunity to present our paper on waste characterization for settlement assessment for surcharge or waste foundation. This is for infrastructure project in Australia. The presentation content includes introduction, waste material, site investigation, and its importance, and then the case study. As shown in figure 1, there are so many waste management facilities in Australia, especially concentrated in populated cities in West Coast, the East Coast, and West Coast. So any transport projects constructed within these populated cities often intersects areas with these waste management facilities with poor subgrades, including underlying compressible material. So stability and serviceability are critical. Settlement of waste is often, that is, settlement means serviceability. Performance is often due to more critical high compressibility and regularly wide distributions. This waste, typically municipal solid waste, highly heterogeneous, highly compressible, highly permeable, but not necessarily a low strength. Set compression mainly of primary settlement due to void collapse, and the long-term secondary settlement due to the mechanical creep and decomposition. Site investigation is very important to characterize the waste properties. It's better to do a stage approach. First, review all the available data, historical data, and waste placement records. Especially these waste placement records, so the as-built information are very important to see the presence of the cell base and the liners. You can use non-intrusive techniques, geophysical techniques, or intrusive techniques such as the boreholes. So geophysical techniques as shown here is very useful, especially to identify the base of cells. A site investigation may consist of boreholes, test pits, and cone penetration tests, etc. So sufficient boreholes with reasonably good continuous sampling is required. As shown in here, in this figure, continuous sample is very important so that we can identify waste constituent, and its proportion with depth. Since we can't take this material to lab due to health and safety reason, all observations should be on site. So we can describe color, odor, as well as estimate weight and volume. Good to take some high resolution photographs so that you can refine your findings later on. Few important properties are the density, moisture content, and organic content. And you can use literature data to get some relationship between the water content and moisture content, so you can refine your findings. And other important in the properties, the waste compressibility index, which is related to moisture content, density, and the organic content, and which in turn related to compression ratio, which is of course very important in assessing the primary settlement. The case study we have we would like to present here is the rail project in New South Wales, Australia. As you can see, existing rail line need to be connected to terminal, and in part of this connection fall over the waste facility, about 295-meter long, out of which about 115 is the northern part is in younger fill, about 15 years old, and the rest is on, or the southern part is on older fill, about 30 years old. However, these older fills are pretty thick, maybe about 15-meter thick landfill. We carried out geophysical investigation as well as the sonic borehole drilling. So each borehole was carefully observed and constituent has been checked. And based on this constituent, we obtained waste, the compressibility index. In addition, we had some information from the trial carried out in 1985. Based on those information, also we carried out waste compressibility index. You can see higher waste compressibility index in 1985 may be due to higher organic content associated with earlier stage of the decomposition. Anyway, based on this waste classification index, we come up with the compression ratio to be 0.15 and 0.2. And then we also adopted creep rate to be 0.015, mainly based on literature showing the relationship between the waste compressibility index. And also there are evidences to say that this related to bulk density of the material as well. As you can see in this figure, this line shows the finish level of the rail line and then the existing fill surface, pretty thick embankment within the new fill area and shallow embankment within the old fill. Due to this thick landfill, we need to have a higher surcharge. Out of many possible options, we decided to go for surcharge. And you can see the constructed surcharge embankment here is pretty high embankment. During this construction, it's very important to have instrumentation and monitoring so that we can assess the performance of embankment and confirm the design. So we install instruments including settlement plates, some here, settlement plates, some here, and few here. To supplement settlement, fair number of hydrostatic profile gauge, which can be used to observe the settlement continuously across these the embankment cross sections, and inclinometers to get the lateral deformations, which will be very useful in assisting the stability of this high embankment, and also some survey monuments to supplement the settlement monitoring. As you can see here, the settlement as the observed is about 900 millimeter. Different settlement plates, as you can see along the full length chainage, you can see higher settlement in the old landfill area where landfill thickness is about 15 meters and the surcharge also pretty high. Back canalized compression ratio is about 0.09 to 0.15, which is slightly less than we adopted, and also these numbers fall within the available literature the limits. We also check the ratio between lateral deformation and the settlements. That ratio is about 10 to 15. So we know that that ratio indicates the reasonably stable despite this very high surcharge or high embankment. As you can see, the hydrostatic profile gauges show some spikes, maybe due to localized collapse of voids across that embankment cross section. What we observe is the completion of primary settlement occur within about 3 months. As you can see here, is very quick relatively, and then it tend to show some secondary settlements start, and because of the some unloading, some unload and then settlements. The back canalized, the creep rate is about 0.01 and 0.19, which is very similar to what we have adopted. This is the project completion. As you can see, the rail track over the embankment, final rail track. Estimated long-term settlement is 500 millimeters. We come up with the railway maintenance program so that we manage the settlement rather than completely adjusting it to 500 millimeter. So in conclusion, the application of conventional site investigation and characterization on waste solid material could be challenging. So we'll have to be very careful how we carry this out. We characterized waste material and then we come up with these properties. Full monitoring is very important. It is primary, very important for the back analysis and the confirming your design. Strain rate is typically related to void ratio and bulk density. And estimation of primary current is critical for the design so that we can design our surcharge thickness. This case study presented indicated reasonable correlation between back-analyzed compression ratio and dimensionless the index, the waste compressibility index. And creep assessment was evident following the completion of critical void collapse, especially during primary treatment. So further monitoring beyond the end of primary so far indicate reasonable observations of creep. Thank you.